गुड मॉर्निंग सर। हेलो। यस सर, गुड मॉर्निंग सर।
है गुड मॉर्निंग सर।
सर एक बार ना आप पीपीटी अपना शेयर करिएगा, अपना कैमरा ऑन करिएगा सर।
हाँ सर, कैमरा मेरा, हाँ एक मिनट जस्ट। आई थिंक सर स्क्रीन विजिबल है क्या?
नहीं सर, विजिबल तो नहीं है सर अभी।
हेलो वासने साहब।
मैंने शेयर कर दिया है।
बट सर स्क्रीन आपका दिख नहीं रहा है सर यहाँ पे। हाँ यस सर, दिख रहा है,
सर
विजिबल है
यहाँ
सर,
से मैंने शेयर
विजिबल
कर
सर।
दिया शेयर।
यस सर, विजिबल है।
ओके ओके।
विजुअल है,
अभी
सब कुछ
स्लाइड्स मूव कर
शेयर
रही
है।
है सर?
यस सर।
ओके सर, ओके सर, ओके।
सर हमारे साथ ये एक्स डायरेक्टर हैं एल के बी एन दीक्षित सर।
नमस्कार सर।
नमस्कार वासने साहब जी, कैसे हैं?
मैं सर ठीक हूँ सर, आप कैसे हैं?
बढ़िया है जो है। तो दिल्ली में ठंड थोड़ी बढ़ गई होगी।
हाँ सर, थोड़ा सा टेम्परेचर बढ़ गया है, कम हो
हाँ
गया, मतलब ठंड बढ़ गई है।
हाँ, वही वही। ठंड बढ़ना मतलब टेम्परेचर कम होना।
कम होना, हाँ।
लेकिन लोग बोलते हैं कि ठंड बढ़ गई।
हाँ हाँ सर।
सबकी भाषाओं की टर्मिनोलॉजी है जो।
हाँ सर।
तो सर जो है आज जो है आप फ्लो मीटर पर बोलेंगे जो है।
हाँ सर।
सो लेडीज एंड जेंटलमैन, all the legal metrology officers who are participating in this very program, scientists, industry officers who are the part of this very programs. Today I welcome Mr. Anshul Vatsne. He is the senior scientist from CSIR, National Physical Laboratory, you know.
यस
So
सर।
he is having the very good knowledge on these very subjects. The flow meter is also the part of the legal metrology.
यस।
With the water meter also, the flow meters also, the various type of flow meters has been prescribed in the specification meter for liquids other than waters. So all those things has been given there. The people might be knowing there, all the enforcement officers who are verifying all these very things. So they are well aware there how to verify all these very things there. Lot of industries are there in various part of in the various part of our country in various states. So particularly in Maharashtra and Gujarat, there are a lot of industries are there. So people are might be getting benefit from those very things. So in weights and measure, if nothing is verified, it cannot be used. So before verification, all the inspector used to go to its premises where the uh, all the standards are there and the under test are there, and on that very bench of the flow meter, these things are being tested. And after testing, it is verified, then it goes to the market for selling and verification, selling and installation, both purpose. So it is not only with the flow meters, you see that there is the uh, dispensing pumps also. Dispensing pumps, which is meant for the flow meters, meant for the petrol measurement, diesel
Yes,
measurement,
exactly.
and CNG measurement, that also is part of the flow meters. So earlier it was the different from the flow meter for liquids other than water. Now everything has been contained. There are the various flow meters which is used for the LPG measurement, CNG measurement, and so many other type of things also, sir. Even for the PNG measurements also, sir. So all things has been defined under the flow meters, sir. Today we have got the very good opportunity that one of the big scientists is before us, sir. So I hope that Anshul Varsne will enlighten all the things that how to measure all these very things and how to test it, how to calibrate it, what the precaution has to be made, and so many other this type of things. So from this very forum, I welcome Dr. Anshul Varsne Saab, sir, and I will request him to start his lecture, sir. Thank you, sir.
Thank you, sir.
Please start your lecture, sir.
Thank you, sir. Thank you very much. I am just closing my camera. Thank you, Dikshit sir, for throwing some light about the importance of fluid flow measurement. So today in this presentation, I will speak about progress and innovation in fluid flow metrology at CSIR NPL. What we are doing at CSIR NPL, what calibration we are providing in terms of water and gas. So I will give some brief introduction about these facilities which has been established as CSIR NPL. So before going into the detail, would like to go through some basics of flow. What are the basics of flow measurement? What is the fluid? What types of flow meters are being used in industries, and which standard is being used for calibration of these type of flow meters? So I will give some little bit introduction about these uh, terms. So, what is a fluid? Basically, for what we are calling fluid. The definition of fluid is a substance in the liquid or gas phase which can flow, that is called fluid. And fluid doesn't mean we are talking about only water. Generally, in normal general terms, people consider water it is a fluid, but any substance which is in a liquid or gas phase that can flow, that is called as fluid. A solid can resist and shear stress by, you can see by this figure. Uh, a fluid deforms continuously under the influence of a shear stress, no matter how small. However, in solids, this stress is directly proportional to the strain, but in fluids, stress is proportional to the strain rate. So when we are applying a constant shear force, a solid eventually stops deforming us at some fixed strain angle. However, in case of fluid, that never stops deforming or approaches a constant rate of strain. It continuously going on deforming as we are applying a strain. So you can see a deformation of a rubber block which is placed between two parallel plates under the influence of a shear force. The shear stress is shown that on the rubber an equal but opposite shear stress acts on the upper plate. You can see from this figure, when we are applying the shear stress, it continuously starts deforming in this direction, in the direction of force at a particular angle of that is called shear strain. So what is stress? Stress is generally known as force per unit area, and normal stress, this is the normal component of a force acting on a surface per unit area, and shear stress. Shear stress is basically the tangential component of a force acting on a surface per unit area, this one. And pressure, the normal stress in fluid at rest. And what is zero shear stress? A fluid at rest is at a state of zero shear stress. When the walls are removed or a liquid container is tilted, a shear develops as the liquid moves to re-establish a horizontal free surface. That is called zero shear stress. In a liquid group of, you can see this in this container we have filled some liquid, and this container there is some gas. So in a liquid, groups of molecules can move relatively to each other, but the volume remains relatively constant because of the strong cohesive force between the molecules. Because of this, a liquid takes the shape of the container it is in. In whatever type of container we are filling the liquid, it forms a free surface, and in a large container it is in a because of gravitational field. However, in case of gas, it expands until it encounters the wall of the container and fills the entire available space. This is because the gas molecules are widely spaced and the cohesive force between them are very small. Unlike liquid, a gas in an open container cannot form a free surface. It will continue expanding until it will not encounter with any boundary or any wall of the container in which the gas is being filled. So now coming direct the application of fluid flow measurement. What are the application of fluid flow measurement? Like process control, nuclear power, aircraft industries, human life, power generation, fertilizer industries, beverage industries, distilleries, liquid industry, irrigation sector, pharmaceutical industries, gas industries, R&D laboratories, pollution controls, petrochemical, agriculture, and dairy paints, and different type of many other industries. Basically, at NPL, we are catering these all types of application to different sectors. So, if we are going in detail, like industrial application, what are the role of fluid flow measurement, monitoring and controlling fluid flow pipelines like oil, gas, water, and chemicals, optimizing fuel consumption in power plants, process control in pharmaceutical and chemical industries. Similarly, in environmental monitoring, fluid flow is used for measuring river and stream flow for flood prediction, monitoring wastewater discharge and pollution control, accessing air and gas emission in industries. For medical and healthcare, like in blood flow measurement in cardiovascular diagnostic, drug delivery system, basically syringe pumps, infusion device analyzers, IV drips, inhalers, these types of devices where fluid flow metrology plays an important role. And respiratory flow monitoring in ventilators, like oxygen concentration, oxygen flow rate, inhale volume, exhale volume. These are the parameters as taken care by fluid flow metrology. In automotive and aerospace, fuel flow measurement in internal combustion engines, aerodynamic testing in wind tunnels, hydraulic system monitoring in aircrafts. Similarly, in agriculture and air irrigation, flow control in irrigation systems, groundwater and soil monitoring, fertilizer and pesticide distribution systems. And in HVAC and building system, it is in air flow measurement in ventilation and air conditioning systems, water flow monitoring in plumbing and heating systems, and energy efficiency optimization in buildings. Where these are the some sectors where fluid flow measurement is used. And these are the some application area of fluid mechanics. Like fluid dynamics is usually extensively in the design of artificial heart. You might have listened about the artificial hearts. So in artificial hearts, fluid dynamics is the major parameter which is used extensively in designing of these type of equipments. This is a basically artificial heart which is developed in Penn State. And another important application of fluid flow, natural flow and weather and power plants. Similarly, in transportation, in water transportation, aircraft and spacecrafts, human body and cars, wind turbines, piping and plumbing system, industrial applications. These are the some important applications where fluid flow measurement is widely used. In our, we can see these applications in our daily life. There are different types of flow which exist, like steady flow. So the flow in which the velocity of fluid is constant and at any point is called steady flow. So this is the example of steady flow. We are measuring the flow in present, and with the help of this present velocity, we can predict the flow velocity at some future points. However, in unsteady flow, the fluid velocity differs between any 2 points. At a particular point, the fluid velocity will be something differ, and at another point, there will be some another. Similarly, uniform flow. In uniform flow, where flow velocity is the same magnitude and direction at every point in the fluid. However, in non-uniform, if at a given instant the velocity is not the same at every point, the flow. In this type of flow, study on STD I have explained earlier. Similarly, study uniform flow. In a study uniform flow where it do not change with position in the stream or with time. The example of the steady uniform flow, the flow of water in a pipe of constant diameter and constant velocity. That is an example of steady uniform flow. Similarly, a steady non-uniform flow, in which the velocity change from point to point in the stream but do not change with time. The example of steady non-uniform flow is flow in a tapering pipe with constant velocity at the inlet. Velocity will change as you move along the length of the pipe towards the exit. Basically, it follows the continuity principle. So now, unsteady uniform flow, at a given instant in the time, the condition at every point are the same but will change with time. The example of unsteady uniform flow is a pipe of constant diameter connected to a pump, pumping at a constant rate, which is then switched off. Unsteady non-uniform flow, every condition of the flow which may change from point to point and with time at every point. The very basic example of unsteady non-uniform flow is waves in a channel. Now, coming to another type of flow, that is laminar. In laminar flow, all the particles proceed along a smooth parallel path, just as shown in this figure, and all particles on any path will follow it without deviation. Hence, all particles have a velocity only in the direction of flow. This type of flow is called laminar flow. Similarly, turbulent flow, the particle moves in irregular manner through the flow field. So each particle has superimposed on its mean velocity, fluctuating velocity components, both transverse to and in the direction of the net flow. So this type of flow is known as turbulent flow. And transition flow exists between laminar and turbulent flow. In this region, the flow is very unpredictable and often changeable back and forth between laminar and turbulent states. So that is called as transition flow. These are some other pictorial example of laminar flow and turbulent flow, how you can understand about the nature of flow. Next, another type of flow is coming, compressible or incompressible flow. All fluids are compressible, even water, their density will change as pressure change under steady state conditions and provided that the change in pressure are small. It is usually possible to simplify analysis of the flow by assuming it is incompressible and it has a constant density. So compressible flow, when the density of flow varies with pressure, it is termed as compressible flow. However, incompressible, when the density of flow does not vary with pressure, it is termed as incompressible flow. Next, another viscous and non-viscous fluid flow. Viscous flow, such as honey, does not flow readily and it is said to have large viscosity. The flow which is having very large viscosity, it is known as viscous flow. However, the fluid with zero viscosity, that is known as non-viscous flow. So there are some fundamental equations of fluid dynamics, like law of conservation of matter. It stipulates that matter can be neither created nor destroyed, as we all know, though it may be transformed by some chemical, mechanical, or electrical process. Since the study of this machine's mechanics of fluids exclude chemical activity from consideration, the law reduces the principle of conservation of only mass. Now, next is law of conservation of energy. It states that energy may be neither created nor destroyed. Energy can be transformed from one form to another. Sometimes engineers, researchers sometimes loosely refer to energy loss due to friction, but in fact, that loss basically transforms some energy into the heat. So nothing is really lost. Whatever you are using at inlet side, you are getting it the output. Next, law of conservation of momentum. It states that a body in motion cannot gain or lose momentum unless some external force is applied. So basically, it is the follows the Newton's second law of motion. Force is directly proportional to the rate of change of momentum. So next we are coming to the continuity equation which we are using in fluid mechanics. Matter cannot be created or destroyed. It is simply changed into a different form of matter. So this principle is basically known as conservation of mass, and we use it in the analysis of flowing fluids. So continuity equation basically based upon the principle of conservation of mass. For a fluid flowing through the pipe at all cross section, the quantity of fluid flowing per second is constant. Or in other words, for a steady and incompressible flow, rate of flow of liquid remains constant and different cross sections. So this is basically you can understand the continuity equation. Is a pipe. Here area is A1, velocity is V1, and density of fluid is ρ1, and at point number 2 area is A2 and velocity V2. So the multiplication basically A1 V1 will be equal to the A2 V2 at all the point of this pipe. Since we are using the same fluid for throughout the pipe, so density will remain constant. So A1 V1 equal to A2 V2. So this principle is mostly used in fluid dynamics. If the velocity, this is the derivation of this. Now I am skipping this part. Now application of continuity equation. So we can apply the principle of continuity to pipes with cross section which change along their length. So basically a liquid is flowing from one point to another point in a narrowing. If we are narrowing the same pipe in the flow direction, so by the continuity principle, the mass flow rate must be the same at each point. Basically ρ1 density into A1 V1 equal to ρ2 A2 V2. So as we are considering a liquid, usually water, which is not very compressible and the density change very little, so we can consider the density at each point same. So this will come A1 V1 equal to A2 V2, or velocity at discharge point will be the you can get V2 equal to A1 V1 by A2. So discharge at section 1 or you can say section inlet will be the equal at the outlet. So another example is a diffuser, a pipe which expands or diverges as in the figure. This is given in this figure. Here in the earlier figure, section 1 area of section 1 is bigger one. However, in diffuser, area of inlet is somewhere less than the output. However, they both are following the continuity equation, and the continuity principle can also be used to determine the velocity in pipe coming from a junction. You can see this pipe is dividing into two parts. So this will A1 B1 will be the equal to A2 B2 plus A3 B3, because as per the principle of conservation of matter, matter cannot be destroyed or generated. The total discharge will be the equal to the total discharge at outlet. The principle, now coming to the principle of conservation of energy. In this, here we are considering friction is negligible and sum of kinetic energy and gravitational potential energy is constant. So kinetic energy is basically half mv square. So gravitational potential energy equal to mgh. So basically if we are considering initial kinetic energy equal to 0, potential energy mgh, and final kinetic energy half mv square, and final potential energy equal to 0. So kinetic energy and potential energy will remain constant. So this is the basically basic example of continuity equation which we are seeing in our daily life. If we are flowing water in a pipe and we are watering our fields, or we are using water for any other application, if we are not changing the area of outlet, the water is flowing at some particular velocity, and we are reducing the area by use of finger or something else, the velocity increases. So it follows the equation of continuity. If we are reducing the area, A1 V1 equal to A2 V2, if you are reducing the A2, the velocity at that point will definitely increase. This kind of fluid behavior is described by the equation of continuity. So there are some energy which are possessed by the following fluid, like kinetic energy, potential energy, and pressure energy. So basically, next very basic thing, basic principle comes Bernoulli's theorem in fluid mechanics. So this theorem states that whenever there is a continuous flow of liquid, the total energy at every section remains the same, provided that there is no loss or addition of the energy. So basically, potential energy, kinetic energy, and pressure energy. So this is potential energy, kinetic energy, and pressure energy. So the sum of these basic energy remains constant at each point. We see that from applying equal pressure or zero velocity, we get the two equations from the section above for different point. They are both just they will be the same at each point. So there are some restrictions in Bernoulli equation, like flow should be steady, density should be constant, and friction loss should be negligible. So these are the some limitations of Bernoulli equations, like it is applicable to ideal incompressible flow. The heat transfer into or out of fluid should be zero. The temperature remains constant so that internal energy does not change. So this is the example of Bernoulli equation. As we are seeing, there is a truck and there is a cover on the truck surface, and truck is stationary. Thus, uh, the cover's surface is totally flat when the truck is stationary, and when the trucks start moving, the cover starts inflating. So this is the example of Bernoulli equation which we are seeing in our daily life and in our household plumbing also. There are some, this is the importance of fluid measurement, like precise and accurate measurement of the quantity of fluid to calculate the correct tariff and to control its misuse, as Dixit sir already highlighted, that like dispenser calibration. So we are also providing the calibration of LNG, CNG and PNG dispensers, which will help to calculate the correct tariff and to control its misuse and safety on environment and health. So these are the some basic importance of fluid measurement in process optimization and efficiency, safety and regulatory compliance, resource management and conservation, quality control in manufacturing, environmental impact monitoring, medical and healthcare applications. Now coming for the points of in what terms we are providing service to the fluid flow measurement. So there are different types of flow meters are available which we are calibrating at NPL. The first time, one example of electromagnetic flow meter. Basically, it works on the Faraday's law of electromagnetic induction, and it is suitable for conductive liquids only. We cannot use this flow meter for non-conductive fluid, because if we are using non-conductive fluid, it will not, there will be no conduction, and the Faraday's law of electromagnetic induction will not apply for non-conductive fluid. So electromagnetic flow meters are basically used to measure the flow rate of electrically conductive fluids. They work on Faraday's law of electromagnetic induction, which states that a voltage is induced when a conductive fluid flows through a magnetic field, and that voltage is directly proportional to the flow rate. Though there are some various parts of these types of flow meter, like magnetic field generation. So the flow meter consists of a pair of electromagnetic coils that generates a magnetic field across the flow tube. As the conductive fluid passes through the magnetic field, it induces a voltage proportional to the flow velocity. Electromagnetic flow meter basically, next is electrode sensing. That electrode placed inside the pipe while detects the induced voltage, and the magnitude of that induced voltage is directly proportional to the velocity of the fluid. With the help of that velocity, you can directly calculate the flow rate or totalized volume. The detected voltage signal is processed by the transmitter to calculate the volumetric flow rate. Basically, this is a one type of transducer which converts the electrical signal into the mechanical signal. So you can easily calculate the volumetric flow rate with the help of that voltage signal, and that flow rate can be directly displayed on the flow meter, or it can send to a control system for further use. So the advantage of these type of flow meters, like it is having no moving parts, because of this low maintenance is required in these type of flow meters, high accuracy and reliability, and it is suitable for corrosive and slurry type fluids, works well for large pipeline as well as small pipelines also. And the limitation is, electromagnetic flow meter can only be used for conductive fluids, and it requires continuous power supply for operation. These are limitations for electromagnetic flow meters. Next type of flow meters is ultrasonic flow meters. Ultrasonic flow meter works on time of flight and Doppler effect principle. It is suitable for both liquid and gases, and at NPL we are providing calibration for ultrasonic flow meter for water as well as gases. For water, we are covering the range from 10 liter per hour to 6 lakhs 50,000 liter per hour, and for gas we are providing calibration for these type of flow meters from 1 standard cubic centimeter per minute to 2000 standard liter per minute. So basically, ultrasonic flow meters measure the flow rate of fluids using high frequency sound waves. They work based on the principle that the velocity of ultrasonic wave varies depending upon the movement of fluid. So it basically the working principle of ultrasonic flow meter is it works on the principle of transit time. Two ultrasonic transducers are placed on opposite side of the pipe in which the fluid is flowing. One transducer sends an ultrasonic pulse upstream against the flow, and the another sends a pulse downstream with the flow. So the time taken for each pulse to travel is measured. The difference in travel time between upstream and downstream signals is proportional to the fluid velocity. So, second type of Doppler type ultrasonic flow meter. So this method works by sending ultrasonic waves into the fluid. If the fluid contains particles or bubbles, the waves reflect back with a frequency shift due to the Doppler effect, and that shift in frequency is proportional to the velocity of the fluid. So these two types of ultrasonic flow meters generally used for liquid as well as gas. So the advantage of ultrasonic flow meters are there is no moving parts similar to electromagnetic flow meter. It works for large pipe diameters and is both suitable for both liquid and gas flow measurement, and it can be used for non-invasive measurement. Non-invasive measurements means if you are using ultrasonic flow meters, there is no need of opening the pipeline or dismantling the pipeline. You can use ultrasonic flow meter above the pipe. You can mount the transmitters above the pipe. The limitation of transit time method requires clean fluid. There should be no bubble or particles. And Doppler methods requires suspended solids or bubbles for signal reflection. Accuracy depends on proper installation and fluid conditions. Like accuracy of ultrasonic flow meters is not as good as electromagnetic flow meters or mass flow meters or any other type of flow meters. And the behavior of these type of flow meters mainly depends on the type of installation. You should know correctly the diameter of pipe, the material of pipe, and thickness of pipe, and the type of fluid which is flowing in the pipe. Until unless you are not knowing these all the things, the performance of this ultrasonic flow meter will not come as expected. This is the way how we are mounting the ultrasonic flow meter. One sensor is upstream side and another is downstream sides. So it works on time of flight or Doppler method. It is used in liquids, water as well as gas. Accuracy varies from 0.5% to 2.5%. However, for electromagnetic, it is 0.1% to 0.5%. This is a multi-path ultrasonic flow meter. Now, coming to another type of flow meters, that is correlate mass flow meter. It works on Coriolis principle and it is suitable for both liquid and gases. This is used as a custody transfer meter and it is the highest accuracy flow meter which is being used. These flow meters comes in the accuracy range of minimum accuracy range of less than 0.05%. Basically, these type of flow meters directly measures the mass flow rate of a fluid using the Coriolis effect. Unlike volumetric flow meters, it provides accurate mass-based measurement, making it ideal for industries where mass flow is critical, like oil, gas, food processing, and pharmaceuticals. So basically, these flow meters consist of following parts like vibration of flow tubes. So you can see there is a U tube. So this is basically a flow. There are two flow tubes. The flow meter consists of one or more U-shaped or straight tubes. An external oscillator vibrates these tubes at their natural frequency. So when the fluid moves through these vibrating tubes, a Coriolis force causes a phase shift or twisting motion in the tube, or you can say there will be some vibration in the tubes. So the amount of twisting is proportional to the mass flow rate of the liquid. So the sensor mounted on the flow meter detect these difference in phase shift between the inlet and outlet side of the tube, and you can the difference in phase shift is directly proportional to the mass flow rate. At our lab, we have observed that if there will be some fake or false detection of phase shift, so that will highly affect the mass flow rate of or result of that mass flow meter. Like if we can take an example of a sugar mill, we are receiving multiple mass flow meters from sugar industries, and sometimes there are some residues or some deposition in the tubes on the U-tubes of mass flow meter. So because of this, that deposition, there will be some shift in the natural frequency of these vibrating tubes, and that severely affects the output of these mass flow meters. So basically, with the help of these correlate mass flow meters, you can easily measure the density, and they can provide built-in temperature sensors for temperature compensation. These are the highest accuracy mass flow meters, as I earlier told. So advantage of these mass flow meters are there is direct mass flow measurement. There is no need of density compensation. The accuracy of these mass flow meters is pretty good, and coming in the range of 0.05%, and it works well for liquid, solids, and gas. There is no moving parts, making it low maintenance. It can measure density and temperature along with mass flow. The limitation is it is expensive compared to other flow meters. It requires continuous power supply for operation and is sensitive to vibration and external forces. In our CNG, LNG, and PNG dispensers, we are using mass flow meter for measuring the flow rate or totalized volume or mass. Next is turbine flow meter. A turbine flow meter is a volumetric type of flow measurement device that measures the flow rate of liquid and gases. It operates on the principle that a fluid flow causes a turbine rotor to rotate, and this rotational speed is proportional to the flow rate. Basically, the fluid flows through the meter, striking the blades of free spinning turbining. So the kinetic energy of fluid causes the turbine to rotate. So the turbine's rotational speed is directly proportional to the flow velocity. And there is a magnetic pickup sensor which detects the rotation of the turbine, and the sensor generates the electrical pulse as the turbine blades passes by. So the frequency of these pulses corresponding to the flow rate. The meter's electronics converts the pulse frequency, the frequency of the pulse, into the volumetric flow rate using a calibration factor. Multiply the frequency by that calibration factor, you can easily get the volumetric flow rate. The advantage of turbine flow meter is the accuracy of is pretty good, between 0.5% to 1%, and these type of flow meters can be used for wide flow range with good repeatability. The are compact and lightweight, and it is suitable for clean liquids and gas, and the response time of these type flow meters is quite good. However, these type is not suitable for dirty and viscous or corrosive fluids. It can damage the turbine, and it requires regular calibration for accuracy, and it is sensitive to flow disturbance and vibrations. Next is rotameter. Basically, it works on the balance of gravity and drag forces. It can be used for water as well as gas. And these type of flow meters are also called variable area flow meter. There is a this is basically a vertical type of device, and there is a scale, and you can see these type of flow meters called is variable area flow meter because the area of this tube varies throughout this section, and there is a float inside the tube. When we start flowing any water or gas, the float start moving in the direction of flow, and it will give you the instantaneous flow rate. The rotometer consists of a vertically oriented tapered tube with a free floating float. The tube is narrower at the bottom and wider at the top. As fluid enters from the bottom, it exerts an upward force on the float, and the float rises until the upward force from the liquid balance the downward force due to gravity. At equilibrium, the float stabilizes at a certain height, the position of the float corresponding to the flow rate, and basically this type of flow meters provide you the instantaneous flow rate. So these type of flow meters are simple and cost effective. There is no external power required. It can work for both gas and liquids. There is a clear visual indication of flow rate, and it is reliable and easy to install. However, these type of flow meters are not suitable for opaque or highly viscous fluids. It requires vertical installation for accurate operation, and it is limited to relatively low pressure applications. Next, orifice and venturi meters. Basically, it works on these type of flow meters are known as differential pressure flow meters, and works on the Bernoulli's principle, which states that an increase in the velocity of fluid results in a decrease in pressure orifice. And venturi flow meters, these type of flow meters are use the principle to measure flow rate by creating a pressure drop in the fluid. If we are considering orifice flow meter, an orifice plate is placed in basically in the pipeline. As the fluid passes through the orifice, the flow area decreases, causing an increase in velocity following the continuity equation, and a drop in pressure. Pressure sensors are placed at upstream and downstream side of the orifice plate. That pressure difference is measured, and that pressure difference is proportional to the flow rate. So this type of flow meters basically use Bernoulli's equation to calculate the flow rate. These are the some flow meters which are used for human health and safety, like infusion device analyzers. These type of flow meters are used in the hospital, and dialysis meters, ventilator tester, syringe pumps, and infusion pumps. So these are the some other types of flow meters which are used for human health. These are from environmental, like respirable dust samplers, stack emission monitoring systems, and wind monitor. The flow meters shown for human health and safety are having other parameters like pressure, temperature, etc. The ventilator tester, basically called as gas flow analyzer, are used to calibrate ventilators. These ventilators are used for providing breathing to the patient during critical care or other applications. So the infusion pumps and syringe pumps are used for drug delivery for patient treatment. The infusion device analyzers are used to calibrate these infusion pumps and syringe pumps. The flow rate used are mostly from 0.12 microliter per hour to 1500 milliliter per hour, which is categorized as low liquid flow or micro liquid flow. So at NPL, we are having this low liquid flow calibration system, and the range of this low liquid flow calibration system is from 1 ml per hour to 1500 ml per hour. So in overall, you can if we are seeing overall, so overall in case of for water calibration, we are providing calibration from 1 ml per hour to 6,50,000 liter per hour, 1 ml per hour to 650 meter cube per hour for water flow calibration, including low flow calibration system. What are the challenges in flow metrology? The challenges in flow metrology are some of the sensors and flow meters are made in India, like electromagnetic turbine and differential pressure, and the performance of these meters are not verified in terms of their accuracy, their repeatability. There are facilities for calibration of the flow meters for liquid medium. For syringe pumps calibration, our capabilities earlier it was from 10 ml, now it is from 1 ml per hour. We are not providing calibration below 1 ml per hour. So facilities are also available for calibration of most of the flow meters for air and gas medium, but facility for high accuracy multi-path ultrasonic flow meter are not available. For such flow meter calibration, we need standards of 0.03 to 0.05% accuracy. So the syringe pumps, infusion device analyzers, ventilator testers, and ventilators are not manufactured in India. Coriolis mass flow meters manufacturers, like Andershauser, Emerson, Krone, have more than 95% share in the world. Majorly, mass flow meters are being manufactured by these companies. Multi-path ultrasonic flow meters manufacturer Emerson is having dominance in this world. So basically, we are not having technology of design and development of flow meters like ultrasonic and Coriolis mass flow meters. We are not having facility for calibration of these flow meters like ultrasonic mass flow meters. So for basically for flow meter calibration, we are using basically the primary method of flow meter calibration is weighing method or gravimetric method. That is a primary method because that is directly related to SI unit, mass and time. So the ISO 4185 it provides the method and other things for measurement of liquid flow in closed conduits using weighing method. So ISO 4185 provides a standardized method for measuring liquid flow using the weighing method. It ensures high accuracy and traceability to national and international standards. It is commonly used for calibrating flow meters and verifying industrial flow systems. The method involves collecting a known volume of liquid in a weighing tank over a specified time period. So the collected mass is measured and the flow rate is calculated. Basically, flow rate, mass flow rate directly traceable to mass and time. What we are doing in calibration of mass, these type of flow meters, we are collecting a known volume water in weighing tanks for a specified time period. So that mass is divided by time, that will give you the mass flow rate. If you wish to calculate volume flow rate, you will divide that mass flow rate by water temp water density at that temperature. At that flow rate, what will be the temperature? We will divide that mass flow rate by that density, and we will get the volumetric flow rate. So what are the requirements? Equipment and setup requirement as per ISO 4185, like weighing tank, you should have large enough to collect a measurable volume of liquid, and calibrated weighing scale. A high precision mass measurement system is required. A timing device is required for calculating the time for filling the water tank. And there is flow diversion system which ensures accurate measurements and during start and stop. A temperature sensor is required for measuring the temperature of water at that particular flow rate, which will help you to calculate the density at that particular temperature. So earlier I told a precision weighing system is required, which uses a scale with a certified accuracy level. Environmental factors minimize effects of temperature, pressure, and vibration. So basically, ISO 4185/1980 primarily focus on the gravimetric method for flow meter calibration and does not explicitly provide detailed installation guidelines for flow meters in pipelines. However, in best practice for installation, flow meters in compliance with metrology standards includes the following points, like a straight pipe requirement. It ensures adequate upstream and downstream straight run piping to achieve a stable flow profile. And it typically 10 to 5 times pipe diameter upstream and 5 to 10 times pipe diameter downstream are recommended. In our lab at NPL, we are using more than 10 to 20D upstream length and more than 5 to 10D downstream length for calibration of these flow meters. Avoiding flow disturbance. So basically, the flow meters should be installed away from pumps, valves, vents, elbow, and reducers that may cause turbulence. If it is not possible to install away from these devices, the flow conditioners or additional straight pipe lengths may be required for accurate measurement. Electromagnetic and next point is orientation of flow meters. Like electromagnetic and ultrasonic flow meters, it can often be installed horizontally or vertically, but must be fully filled with liquid to prevent air pockets. However, for turbine and vortex flow meters, it preferably installed horizontally to maintain stable flow and conditions. And for correlate mass flow meters, orientation depends on manufacturer's recommendation, but it should avoid installation where air or gas bubbles can accumulate. There should not be any air or gas bubbles in U-tubes. Mounting considerations, ISO 4185 states that one should ensure proper alignment of flanges to prevent misalignment stress. Use vibration isolators if installed in areas with high mechanical vibrations. Install support structures for large or heavy meters to avoid strain on the pipeline. Avoid excessive temperature variations that may affect meter accuracy. Install pressure and temperature compensation devices if required for accurate density correction. Ensure proper protection from direct sunlight, moisture, and corrosive environment. For outdoor installation, use protective enclosures or weatherproof housings. Uh, Provide access points for periodic calibration and maintenance. Flow meter should be installed in location where removal for recalibration is feasible. So these are the basic guidelines which has been provided in ISO 4185 for calibration of flow meters for measurement of liquid flow in closed conduits. And there are some additional standards for flow meter installation like ISO 5167. It provides the guidelines for flow measurement using differential pressure device like orifice and venturi flow meters. ISO 6817, it provides installation of electromagnetic flow meters. ISO 4064, it provides the guideline for installation requirement for water meters. So as per ISO 4185, there are some error source like improper timing measurement, leaks in the weighing tank, bubbles affecting density, uncertainty calculation. ISO 4185 provides guidelines for error estimation. So the application of ISO 4185 is it is used as a reference method for industrial and lab testing. It is used for verification of flow rates in pipelines. It ensures precise liquid flow control and high accuracy fluid measurement. It helps in high accuracy fluid measurement studies. And it is not suitable for real-time monitoring. And it requires precise instrumentation setup, high operational costs compared to other flow measurement methods. The conclusion of ISO 4185 is ISO 4185 ensures accurate flow measurement using the weighing method. It is widely used for calibrating flow meters in industrial applications. A proper setup, calibration, and environmental control are critical for accuracy. Despite limitations, it remains a gold standard for flow verification. So I earlier told how we are calculating the mass flow rate. So basically, in weighing method, mass flow rate basically is mass by time. In volume flow rate is basically mass flow rate divided by density that particular temperature. There are two types of measurement methods, like weighing method and volumetric method. In weighing method, there are two types of weighing: static weighing and dynamic weighing. So static weighing uses flying start and flying finish. In static weighing technique, the mass of the collected water is measured after achieving the steady state of the collected water. It is the most accurate method for flow measurement all over the world. However, the water flow measurement and calibration facilities are being used on this method due to its high accuracy. Static weighing is also used in standing start and dynamic standing finish. However, in dynamic weighing, in this dynamic weighing method, the mass of water being collected in a collection tank is continuously measured as a function of time. The slope of that mass time curve directly will give you the mass flow rate. But the accuracy of dynamic weighing is not as good as static weighing. So this is basically a schematic diagram of water flow calibration facility based on static weighing. You can see there is a constant level overhead tank, and this is a weighing tank. This is weighing scale, and this is sump. Basically, water is coming from the overhead tank to the tank with the and there is a diverter. This is a very important part of flow measurement system. The earlier the water is flowing through this bypass line, through this diverter. When we divert flow into this weighing tank, water starts filling this tank, and when we stop filling, the mass of this water is measured, and the filling time, that mass is divided by the filling time, and you will get the mass flow rate. So this is basically direct another method. This is basically a dynamic weighing. We are flowing this water tank, and the weighing weight of this tank is continuously measured during the flow. Next method is volumetric method. In volumetric method, the water flowing through the meter under test is collected in a volumetric vessel for a predetermined time, and its volume is measured. So, thus, volume flow rate is derived and calculated. Since the determination of volume flow rate is measured indirectly from mass, it is called as a secondary method. If the volume flow rate is determined in fundamental unit of length and time and does not require density measurement, it is called as a primary method. So there are two ways of static weighing, like standing start and standing finish, and next another one is flying start and flying finish. So this is basically standing start and standing finish method. So this method is best suited for totalized type liquid meter and flow. However, in this type of method, meter and flow control valve response should be as fast as possible. A minimum collection time for standing start and standing finish method is 60 seconds. However, in flying start and flying finish, timer starts and stops with movement of diverter. This method is suited for flow rate type liquid meters and is suitable for flow meters having slow response. And minimum collection time for this method is 30 seconds as per ISO 4185. So these are the some part of but our water flow calibration facility, like flow generation system. Flow generation system basically consists of storage tank, constant level overhead tank, pumping system, and a flow control system. A storage tank basically used to store large quantity of water to be pumped to the test section and ultimately reaching to the same place through weighing system or bypass line, thus completing closed loop cycle. At NPL we are having 3 pumps of 50 HP. Capacity of each pump is 2,50,000 liters, and another part of this system is a 15 kilowatt air compressor with dryer and control panels for pumps and manifold valves. There are some pneumatic valves are used. So the compressor supplies air for opening and closing of that pneumatic valves. There is a overhead tank. The capacity of this overhead tank is 21,000 liter, and the height of this overhead tank is 25 meters. When water falls from 25 meter, it will provide you the continuous absolutely stable flow if your water is falling from 25 meter. Next is test section. Basically, test section is basically a piping system producing the required flow condition for the meter under test. The main purpose of this system is to obtain appropriate and fully developed flow for flow meter operations. Therefore, flow conditioners are installed upstream of the flow meter and away from the meter under test to avoid any flow disturbance that might affect the meter performance. So this is the test section, so which is showing flow meter upstream and downstream length. This is the flow meter which has been mounted for test. This is the upstream length and this is downstream length. Next part is weighing system. It is basically a precision balance with collection tank. So that the diverter is considered as a part of the measurement system. This is used to direct flow either into the collection system or into the bypass. So this is our old system in which we are having DN50, DN100 and DN200 lines, and we are using this type of tanks in our old system. And these are the sources of uncertainty in water flow calibration using weighing method are like relative combined distance of volume flow rate, and this is the uncertainty for collected liquid mass. This is URT uncertainty for collection time, and this is for density. So the factors which affecting the uncertainty of collected liquid mass are balance indication, balance drift, balance calibration, buoyancy correction, leaks and splashes, storage effect, and evaporation. Similarly, for collection time, like timer calibration, timer actuation, diameter error, and for liquid density, like densitometer calibration, quality of the liquid, temperatures of liquid. These are some factors which are affecting the uncertainty of overall system. The collected mass, the uncertainty of the collected mass basically depends on the balance indication, balance drift, balance calibration, and buoyancy correction also. So you can use calculate the density and other things also. Collection time, the uncertainty of the collection time depends on the timer calibration, timer actuation, and the diverter error. For high precision timer, its calibration uncertainty is negligible, and collection time uncertainty is dominated by the diverter error. So diverter basically plays an important role in water flow calibration. So basically, for a accurate diverter, the for you can say for calculating the flow rate exactly, the diverter error as minimum as possible. Basically, if you are considering the collection flow from T0 to T5, so for error free condition, this time this area should be equal to this area. A plus D should be equal to B plus C. If it is not equal to there should be you can say diverter error should be as minimum as possible for error free transition. So this is the mathematical formula. With the help of this standard formula, this is given in ISO 4185, and with the help of this we are minimizing the diverter error at our facility. Basically, we are having three weighing scales. One is 300 kg, one is 3000 kg, and another is 6000 kg. So error of 300 kg is 2 grams only. Error of 3000 kg is 50 grams, and error of 600 kg weighing scale is only 100 grams. So we are having three diverters, and we are regularly, after each month, we are calculating the diverter error of all the diverters. So if diverter error is coming more than the specified limit, we are adjusting that proximity switch of diverter to minimize the diverter error. So there are the main factors to improve the performance of a water flow calibration system are to improve the water flow stability using constant level overhead tank for flow conditioners, to improve the timing errors using self-cancellation or error-free diverter, and also using of large size of collection tank to develop better instrumentation and control for achieving improved accuracy. So in a highly accurate water flow calibration facility utilizing traditional diverter, the diverter timing error is a significant source of uncertainty as compared to other components like mass and density of the collected meter. This is basically a diverter. It is called fish-tail diverter system. You can see before this fishtail there is a thick line of water is coming, and in this section that water line is spreaded to avoid any water splashes during filling tank. So this is basically PC base, old PC base, our control panel PC based measurement system. This is the program developed in LabVIEW for measurement of flow rate. This is diverter error calculation, and this one is this is our upgraded primary flow calibration facility. Right now we are providing calibration in this facility. So basically we are having 6 pumps, 3 pumps of 50 HP and 3 pumps of 3 HP, 5 HP and 10 HP. There is a underground water tank. So the capacity of this ground water tank is 2,25,000 liter, and the length dimensions of this water tank is it is 30 meter in length, 3 meter depth and 3 meter width, and there is a overhead tank of 21,000 liter. It is at the height of 25 meter, and we are having 5 dedicated lines, 25 mm, 50 mm, 100 mm, 150 mm, 200 mm, and we are providing calibration in this facility from 10 liter per hour to 6,50,000 liter per hour, and we are having, I earlier told, we are having 3 scales. This is the pictorial diagram for our butter flow calibration facility. The range is up to 650 meter cube per hour, and uncertainty is as 0.03% to 0.05%. This is the control panel. These are the display for weighing scales: 3000 kg, 300 kg, 3000 kg, and 6000 kg. This is a 4 to 20 milliampere digital multimeter. This is frequency counter, and these are the display for different reference flow meters. This is basically a timing device. This is HMI, basically human machine interface for pumps and valves. Electrical panel. This is electrical panel for compression and manifold valve operation. This is HMI for pumps and valves. We are using a N10 power offline digital density meter for water density calculation. It is the world's best density meter, having the accuracy of 0.0005%. It has capability for temperature scan and provide temperature versus density table. This is the frequency counter. Every flow meter is having 2 types of output, either frequency output or current output. So for current output we are using this digital multimeter, and frequency output we are using frequency counter. The space link triggering circuit has been developed for frequency counter and digital multimeter for averaging and totalizing of flow meter output in real time triggering. And for our weighing system verification, we are having different types of weight. So for some specific period of time, we are verifying the performance of our weighing scale with the help of standard weights. Like you can see, for 300 kg it is exactly showing 300 kg, and for 3000 it is exactly showing 3000 kg, and for this is for 6000 kg. We are having standard weights for the verification of these our weighing scales. But this is the basically diverter error, percentage diverter error of 300 kg weighing system for different flow rates. Or diverter error is quite small. The sources of uncertainty for electromagnetic flow calibration in frequency mode, like weighing time calibration, resolution of weighing scale, buoyancy correction, timer calibration, diverter error, butter density, frequency counter, and repeatability. This is the way how we are mounting the flow meters in different lines. Like this is in 25 mm, 50 mm, and 150 mm. Now we are having calibration facility for biomedical instruments, which is called low liquid flow calibration system, also supporting which is supporting biomedical laboratories in the country by providing calibration of biomedical instruments like infusion pumps, infusion device analyzers, dialysis meters, etc. This part I am skipping. Basically, these are the calibration procedure for rotameters and mass flow meters. Basically, we are using the gravimetric method for calibration of these all the type of flow meters. For rotameters, we are using the standing start and standing finish method, and for other flow meters like mass flow meters, magnetic flow meters, and turbine and vertex flow meters, we are using flying start and flying finish method. In spite of this, we are having gas flow calibration facility also. The range of our gas flow calibration facility is earlier. I will talk about water meter testing facility. We are having water meter testing facility. We are providing water meter testing service for as per IS 1779, IS 6784, and ISO 4064. to the water meter manufacturer company, state boards, state governments, water boards, etc. Basically, we are providing water meter testing from meter size from 15 mm to 200 mm. This is our water meter testing facility. This is pumps for supplying the water, and water meter which is being tested mounted here. And different types of tests are performed on water meter testing facility, like pressure tightness test. So the meter is subjected to hydrostatic continuous water pressure of 1.6 megapascal for 15 minutes and 2 megapascal for 1 minute. So when only the meter has qualified for the above, it is subjected to other tests like accuracy test. So accuracy test is done basically minimum flow, transitional flow, nominal flow, and maximum flow. Next, loss of pressure test. The meter is tested for loss of pressure within the meter at nominal flow rate and maximum flow rate. The loss of pressure should not exceed 0.025 megapascal and 0.1 megapascal respectively at the two stages. Temperature suitability test. After accuracy test, the meter is placed in the constant temperature bath meant for temperature suitability test, maintained at 45 degrees centigrade plus minus 1 degree centigrade. It is kept there for 10 hours while the meter is immersed in water. After 10 hours of continuous immersion at 45 degree plus minus 1, the meter is taken out and kept for some time in the open to acclimatize it at ambient temperature. It is then again tested for flow test and pressure tightness test. So this is a low temperature water bath system. Live test. Basically, after undergoing the above test, the meter is subjected to live test as per the values given in the standard. Basically, continuous flow test. The test consists of subjecting the meter to constant flow rate as per specified in the table, and discontinuous flow test. This is the basically for discontinuous test. Number of instructions should be 1 lakh, and nominal flow rate basically 10 kiloliter per hour, and for continuous it is more than 10, and period of operation of test basically 800 hours and 200 hours for continuous operation for nominal flow and double of nominal. So this is the some results of accuracy and pressure less for one specific type of meter. Now coming for gas, so we are having gas flow measurement range from 1 standard cubic centimeter per minute to 2000 liter per minute. Basically, for water flow calibration, we are having primary method where we are providing calibration with the help of this gravimetric system or weighing system. In case of gas flow, we are having secondary standard. Basically, this is working on the comparison method. However, we are in the process of developing primary standard for gas flow. So this is some flow terminology in terms of gas, like density, a measure of mass per unit of volume, its units kg per meter cube. Specific gravity, the ratio of density of material to the density of water or air, depending on whether it is a liquid or a gas. Compressible, non-compressible, I have explained earlier, and mass flow rate, volume flow rate also. The very important parameter is Reynolds number. Basically, it is a ratio of inertial force to the viscous force. It is used for determining the dynamic property of fluid to allow an each equal composition between different fluids and flows. Basically, with the help of Reynolds number, we can identify the flow is laminar or turbulent. If Reynolds number is greater than 1, the flow is dominated by inertia force. If Reynolds number is less than 1, the flow is dominated by viscous force. You can see the visualization of flow for different Reynolds numbers. If Reynolds number is 0.05, basically it is dominated by viscous force. If as the Reynolds number increases, the flow is dominated by the inertia force. If Reynolds number is less than 2000, the flow is laminar. If Reynolds number is greater than 4000, the flow is considered as turbulent flow. However, between 2000 and 4000, it is considered transitional flow. Sometimes it is laminar, sometimes it is turbulent flow. One knowledge I have earlier explained. So basically, gas flow applications. The typical device under test for gas flow system are having following applications like mass flow meters, mass flow controllers, rotameters, bubble meters, turbine meters, totalized flow meters, flow orifice, and leak rate monitors. So there are we are providing service through mass flow meter manufacturers and their service centers like Brooks, MK, Sierra, Hastings, and so on. Any process with lots of mass flow meter, biopharma industries, fuel cell testing, environment and quality monitoring, automatic emission testing, nuclear power industry, aerospace, petrochemical and research plants, specialty gas companies. So these are the some device under test which are used for gas flow system, like mass flow controllers, rotameters, critical flow orifice, automotive emission testing, leak rate testers, leak rate monitors and turbine meters, which are being used in gas flow system. The primary standard of gas flow systems are piston prover, valve prover, PVTT and gravimetric time. Their traceability are established in fundamental units of mass, length and time. So traceability of PVTT and gravimetric standards are established in fundamental unit of mass and time, whereas of piston prover and ball prover are established fundamental units of length and time. Right now we are NPL are not having primary standard for gas flow, but we are in the process of development of this PVTT standard, which is primary standard for gas flow. So basically this project is funded by the BIS, and with the help of BIS, we are in the process of development of this primary standard for gas flow, which is PVTT. PVTT basically known as pressure, volume, temperature, and time standard. By the end of 2026, this primary standard for gas flow will be developed in NPL in-house. As I would like to tell you that PVTT is not available commercially in anywhere in the world. So we are developing this standard completely in-house and completely in India. So by the end of next year, this system will be completely functional. So this is the piston prover. These are the other standards for gas flow. Primary standard like piston prover, valve prover. This is basically a PVTT system. This is the NIST USA PVTT system, and gravimetric systems. However, if you are the major disadvantage of this piston prover, valve prover, and this gravimetric system is whenever you are purchasing this system from some whenever you are purchasing these readily available system, if any problem encounters, you are dependent on the manufacturer or service provider. However, if you are developing the primary standard completely by yourself, there is no problem of dependency on others. You can rectify the problem in-house easily. So there are two types of calibration standards, like primary standard and transfer standards. So, the key features of primary standard: it uses the primary measurement as principle, and there is minimum absolute uncertainty. And transfer standards the key features is its precision, stability, ease of operation, lower cost, real-time output, large range of operating conditions. So basically, this is the traceability chart of gas flow measurement system. Like primary standard are piston prover, valve prover, and PVTT or gravimetric time method. Uncertainty is 0.20% or better. Working standard laminar flow elements critically through venturi and turbine meters. Uncertainty is 0.5% or better. And as industrial instrument, the mass flow controllers, rotameters, swap meters, etc. Uncertainty between 0.5% to 5%. So gases are compressible, as we all know. Gas density changes with temperature and pressure, and both of these will change throughout a plumbing system. An accurate direct comparison of gas flow without accounting for density is impossible. So nearly all gas flow process depend on mass flow, not volume flow. So mass flow measurement is critical to gas mixing, chemical, leak rate monitoring, chemical vapor deposition, etc. So mass flow is basically mass divided by time, as earlier told, and volume flow, it is easier to measure directly and visualize than mass flow. The traditional instruments measure volume flow. Volumetric flow units are cubic centimeter per minute, milliliter per minute, liter per minute. So mass flow is never equivalent to volume flow. Mass flow is frequently expressed in volumetric flow units, like FCCM is a unit of mass flow, CCM and ACCM are unit of volume flow. Where S stand is for standard, and so basically gas flow system works on the these some following law, like Boyle's law. So Boyle's law states this P1 equal to P2 due to as constant temperature. It states if temperature remains constant, the change in volume is inversely proportional to the change in absolute pressure. So this is basically a pictorial diagram. If temperature remains constant, so you can easily draw the curve between change in volume. Similarly, this type of plot you will get for Boyle's law for fixed temperature between pressure and volume. Similarly, for Charles' law, if pressure remains constant, the change in volume is directly proportional to the change in absolute temperature. With the help of Charles' law, you can plot the data between temperature and volume. And if you are combining Boyle's law and Charles' law, so you will get this type of relation: P1 V1 equal to T1 equal to P2 V2 by T2. For ideal gas law, ideally all gas adhere to relationship that their PVTD properties are related by the simple equation either PVI constant or PVI NMR. However, if D is expressed volume per unit, then the value for R varies for each gas, and you can write PVIT equal to constant. So this is basically ideal gas law. Basically now I am coming directly to the standards which we are using at NPL. This. Basically, we are using mole block or mole works transfer standard for calibration of gas flow system. It's we are having range from 1 SCCM to 2000 liter per minute. This is the basically mole block terminal, which this basically works on the principle of differential pressure. We are measuring it upstream pressure and downstream pressure, and with the help of this upstream and downstream, directly flow rate can be calculated. This is the expression of mass flow of a compressible fluid in laminar flow through an annular path way. These are some mathematical calculation. Basically, sonic flow nozzle or critical flow venturi is used for the calibration. Sonic nozzle is basically accepted internationally as a flow measurement standard, and flow meter, which is originally used by the aerospace industry. Sonic nozzle are now utilized for many diverse applications in the automotive, energy, and metrology industries. Sonic nozzles can be used as a calibration standard for gas flow meters or any flow measurement device. So by design, sonic nozzle are a constant volumetric flow meter. However, with the use of a regulated pressure supply, the sonic nozzle becomes a state-of-art mass flow meter. The geometry of critical flow venturi is such that the gas is accelerated along the circular arc converging section, and then it is expanded in a conical diverging section, which is designed for pressure recovery in the throat or minimum area point of the sonic nozzle. This is basically a schematic diagram of a critical flow venturi. These are the critical flow venturi. This is basically sonic nozzle. This is internal structure of sonic nozzle. Thank you. Any questions?
Thank you, sir. Thank you. Request you to all participants, please switch on your camera.
Hello,
हेलो
hello, Dr. Ansul Saab.
हाँ बताइए सर.
I is over, no?
Yes sir, my side is over.
So I am very grateful that you came today for this very program and you presented the very nice lecture on the flow measurement. Everybody who participated in this very programs were benefited. Kindly share your program with our departments so that all the participants may get the benefit of that very topic.
Sure
Thank
sir,
you.
I will share the PPT.
Thanks. Lot of thanks
Thank you
for
sir.
coming to this very program. We'll call you time to time again, Jay. And I hope it was very successful. And in near future, we will call the again more stakeholders and organize the program. So